Okay, a ball of mass 1.5 kilograms, that's this guy, is moving downward, okay, down, at 3 meters per second as shown in the diagram. It runs into a second ball of mass 0.6 kilograms that was initially at rest. If ball 1 rebounds and bounces, that means bounces backwards at 1 meter per second in the opposite direction it started. Need to find the velocity of ball 2 after the collision. Okay, I see the word collision. It makes me think momentum. I'm going to need to set up a conservation of momentum. Momentum is conserved in our collisions. And so it looks too like we've got a downward direction and an upward direction. So maybe we can make the downward direction negative and the upward direction positive. Doesn't matter which way you make negative and positive, but you do just have to tell your grader about your signs. So I'm going to do part A here, and whenever I'm doing this conservation of momentum problem, I'm always going to start off by drawing a before picture of what both objects are doing and an after picture of what both objects are doing. And I'm going to put arrows on it to help me with my signs. So before they collide, I have object 1 moving downward and object 2 at rest. And after they collide, I have object 1 bouncing back in the opposite direction. And object 2 is now going to start moving downward to make sure that my total momentum stays constant. Okay, so this is 3 meters per second downward, and ball 1 bounces back in the opposite direction that it started at 1 meter per second. So now I can look at this problem. I see that it's an elastic type of collision. And in that elastic type of collision, the objects start separate and end separate, and they bounce off of each other. I'm going to say that the total combined momentum of the system before the collision is equal to the total combined momentum of the collision after the system after the collision. And so it's because there's no external forces acting on it. There's no friction, there's not a ramp, nobody came in and grabbed the ball and threw it. So the total momentum has to be conserved. It just trades between them. So I'll set up M1V1 for the momentum of 1, and now to solve for the momentum of the second one, I'm going to just keep using the equation for momentum of each object. So let's see, object 1 had a mass of 0.5 kilograms, and object 2 had a mass of 0.6. So I'll do 0.5 kilograms at 3 meters per second, but wait a minute. Notice how I've got arrows on these. Let's take a minute to look at these arrows and say that we decided that the downward direction was going to be negative. So I'm going to plug this in as negative 3 meters per second here times my 0.5. All right, plus 0.6 times 0 equals, now after the collision, this 0.5 kilogram ball is moving upwards in the positive direction. So I'm going to put a positive 1 here, plus 2, which is 0.6 kilograms still, but I don't know the second velocity. That's really what I'm trying to solve for. So what I'll have to do is do 0.5 times 3, which is negative 1.5 plus 0 equals 0.5 plus 0.6 V2. All right, and now I'm going to have to subtract 0.5 from both sides. So negative 1.5 minus 0.5 is negative 2 equals 0.6 V2. And so looks like I'm going to get a negative velocity because negative is in that downward direction, and that's what I was expecting, was for V2 to be moving downward, and downward is indicated with that negative sign. So V2 is going to be equal to 2 divided by 0.6, so it's going to be negative, because it's downwards, 3.3 meters per second. Okay, so the speed is 3.3, the direction is downward. That's why we got this negative value for our velocity of the ball. And now for part B, find the force of tension in the string as ball 2 now moves in a circle. So ball 2 is going to start moving downwards, which is tangent to this circle. And as it's moving at this new velocity, the goal is to find the tension in this string right here. So I'm going to draw myself a new picture for part B that has just ball 2 and the string, and it looks like that is on a table. And so while it's on the table, I've got this ball on the string that's going to be going in this circle. And so while it's on this horizontal table, this is a horizontal surface, and anytime I'm trying to find forces or even acceleration, my step is going to start off by drawing a force diagram. And so as I look at the forces acting on this ball that's on a table, it's got gravity pulling it down. It's got the normal force supporting it upward, and those two are going to balance out because the ball's not accelerating up or down. We know in circular motion the ball is going to be accelerating inward towards the center of the circle. There needs to be a force pulling it inward towards the center of the circle in order to make it turn. And so this force is going to be the force of tension from the rope. And so that force of tension is the thing that's going to make the ball change its direction. Remember, the ball started at rest, but then the ball gets knocked by another ball and it starts moving downward. And it would keep moving downward forever if it didn't have a force inward towards the center to make it turn. So we're going to say that this force of tension is our net force, but because it's causing our circular motion, we call it our centripetal force. And so we could set our force of tension equal to the same equation we use for centripetal force, which is mv squared over r. So in order to solve for our force of tension, we need to know the mass of the ball, we need to know the speed of the ball, and we need to know the radius of the circle. Well, it turns out that the speed of the ball was 3.3 meters per second. That's what we found earlier. The mass of the ball was given as 0.6. The radius of the circle, well, they give us the length of the string, and it turns out that the length of the string is the distance from the center of the circle to the ball, and so that's also the radius of the circle. The radius of the circle is 0.7 meters. So now that I have this all set up, I could say that that's equal to the mass of the ball of 0.6 times 3.3 squared. So I could put in that negative sign if I want to. I can leave it off because it's squared. And then I'm going to divide it by the radius of the circle, which we said was the length of the string. And so that's going to be 0.7 meters. So again, the length of the string and the radius are both 0.7 meters. So now I just have to do 3.3 squared, which looks like 10.89 times 0.6 divided by 0.7. And so I get that my force of tension, or my centripetal force, is 9.3 newtons.